Good morning, everybody. My name is Paul Ian Kavasag, and today I'll be talking about my term paper. And it's called the Multifunctional Smart Ball Sensor for Wireless Structural Health Monitoring in Fire Situation. And the impetus of me wanting to present this is primarily because of the environmental aspect of a critical fire scenario. And when it comes to structural health monitoring, there's a lot of environmental operational variability that is involved with its sensing capabilities. And there's not a lot of papers and systems out there that I know that are capable of withstanding very high fire temperatures and that do not have any effects on their sensing techniques. So without further ado, let's begin. So to just an overview of some of the topics I'll be talking about. It'll vary from giving you guys a motivation as well as background of the experiment of this paper on the right, as well as the results that were yield from the experiment and how we can apply it and maybe some advances and shortcomings in that. So before we can even talk about this sensor, let me just motivate some of the reasons why we should be using this new type of smart ball sensor. And I'll be calling it SBS from now on, just for short. And mainly, in the last 20 years, there's just been a lot of fires that are associated with airport hangars, or as we sometimes call pre-engineered buildings, PEB. From left to right here, you can see there's this George Airport hangar in Canada. And then next you'll see there's the Hooks Airport hangar here with a very high smoke content, and this Monmouth Airport hangar here, which is a post-fire event that happened just recently. So the collapse vulnerability in a fire situation is very present for PEB buildings. And the main reason why is this high temperature can be experienced that range from 300 to 1500 degrees Celsius and can pose as a life-threatening factor for firefighters in extinguishing action of property damages. And for the most part, airport hangars are meant for storage. And what you can surmise probably for these types of structures is they're very fire induced, and they're a life safety and property protection issue because within these structures, there are highly ignitable combustibles. And what can they be? They can vary from fuel storage, as well as like airport commodities such as airplanes, maybe military components, and also not the one aspect here that doesn't really get mentioned that much is minimal security. Because the hangars and PEB buildings are meant to store things. There's not a lot of occupancy, and oftentimes the detection and notification aspect for a fire department might fall off the cracks. And the third point here that I wanted to mention is many structural health monitoring SHM systems are only meant for ambient temperatures. We've learned this in class where there's just a lot of environmental operational variability, EOV, that's associated with sensors and how that they can be damaged and they can provide inaccurate results due to the presence of high and critical temperatures. So not only that, there may be some sensors out there, more advanced sensors that can be implemented, but the one thing that is a disadvantage is just the time-consuming aspect, and as well as the highly prohibitive cost of installing them for pre-existing buildings. So with that in mind, let's give you guys more of a background of just a summary of what this experiment or what this sensor really entails. So this smart ball sensor can immediately install on surfaces of structures, mainly for PEBs, and they're very stable in measuring vital SHM data in real time. So they're wirelessly transmitted as well as with any other SHM sensor. And the one thing that's really great, and probably the mantra that you're going to hear oftentimes here, is that this SBS was meant and experimented and validated for data acquisition in high temperature fire situations. So this SBS, what does it entail? Why is it very highly regarded for high temperature situations? Well, it consists of a sensor and data transmission module. It also has a very thick heat insulator, which I'll also see when we talk about more. And it also has a memory foam. And memory foam is mainly for impact absorption properties. I'll point that out in a little bit. And it has some adhesive module, which is a very lightweight and compact configuration as well. With this integrated device configured, the SBS can be strongly attached to the target surface with a maximum adhesion force, as shown here, and stably detect vibration, acceleration, and temperature of the surface of the structure without damaging the key modules of the system, even at high temperatures, up to like 500 degrees Celsius, while ensuring wireless transmission of data. And in high critical fire scenarios, which may exceed this 500 degrees Celsius, the fire resistance of this sensor can be increased by just thickening the amount of fire resistant material that is made of. And in the end, we'll talk about these field tests for this model PEB structure, scale structure that demonstrated the validity of the SBS and as an instantly deployable high temperature SHM system by the use of drones. So just to talk about these pictograms here, this shows a cross section of the SBS, and it consists of like 3 different types of insulators. There's pyrogel, alloy, and silica fabric here. And you can see from the bottom here is what it looks like on the outside. And it's a very thick insulation. These 3 types of materials here were selected due to their very low thermal conductivity, and they present a good insulative effect for our sensors, which you'll see later on. There's going to be a thermal profile that will prove the reason why these types of materials are good for insulating our sensor here. And on the bottom here, you can also see. So in terms of deployment, one of the ways that is hard during a fire scenario is firefighters tend to perform like fire suppression and search and rescue, but the structure itself can be very vulnerable. So one of the ways that this SBS can be deployed is via the use of drones, and you can just fly this via GPS to any location and drop this SBS to any surface of the PEB structure, so which is shown here. And so as it is dropped, another aspect that needs to be tested is its impact capabilities, besides just its temperature resistance. So both of these we'll talk about, especially for the future extraction as well as the data normalization. So to move on, let's talk about first to kind of give reason to the operation evaluation. So the main thing here is environmental. Ambient temperature, structural impact, and fire suppression agent can affect sensor measurability and data acquisition. SBS sensor packaging materials from pyrogel, silica fiber, and alloy, as I mentioned, have a low thermal conductivity and high maximum operating temperature to protect the sensor module from intense heat of the surroundings. And this SBS has a strong initial attractive force via a magnet between the device and target surface, while it retains a persistent force via an inorganic adhesive at a high temperature to ensure firm, solid contact during the device's operation, to be able to deploy on a targeted surface on the PAB from distance and firmly fixed to the surface. And the SBS as well can continuously function after a structural collapse and fire water extinguishing agent, which I'll show you guys as part of the results. So just to talk more about this, so as you can see here in A, as I mentioned, this can be deployed automatically without a firefighter, and it can be flown to any surface of the PEB, and can be detected via wireless connection. So it's very highly versatile, and it's not affected by what place you have to put it, because you don't have to be there. You can just use this a GPS that's automatically flown with it. If you guys know what a drone is, and it drops it onto any surface of this PEB structure. And as shown here in B, you can see this is the another isometric cross-section cut of the SBS. And this here, the sensor module is just a plan view of its components. You have this battery here, lithium battery, which is a good thing about lithium batteries. It's highly resistant as well to fire. And this GPS, I know it's optional, but I think it'll be a good thing so that you can locate where this SBS is in the structure if you have to be remote. And the Wi-Fi, as I already mentioned, you also have this accelerometer and then thermometer, as well as like some thermocouples and some vibration, and there's some space here still. So mainly this SBS is can be implemented with various sensors, and because of its thick insulator here, it won't be affected by the fire, such as what's shown here. So this is the thermal capabilities. This memory foam here is its impact capabilities, and lastly here, as you can see, is this adhesive module. So to account for the fact that is being attached to a building that may be damaged from an earthquake or from the fire, which is very unstable. What was taught during this experiment is to having to implement this highly adhesive material that even during an effect of a fire, or when the structure becomes unstable, it doesn't get thrown off. So besides environmental evaluation, there's also the operational evaluation. So firefighting and search and rescue operations are not hampered and improves life safety and property protection, as I mentioned. And due to this, you can increase business operation functionality for the airport and continue operations. And SBS can predict structural health status and give alerts to firefighters to prevent possible casualties either from structure collapse or when a fire does flash over, or if there's a backdraft that occurs, which is very hard to detect for firefighters. So this right here is good for operation. So by continuous monitoring of structure health, firefighters can anticipate fire or structural failure and arrive on site earlier. One of the things that's hard to like as I already mentioned is that this PV can be out in the middle of nowhere, remote, and you might not have any fire department that's close by or in proximity. So by having this SHM feature, we'll be able to actively detect when really a fire did ignite or when the structure is failing during an earthquake. So there's not a lot of false alarms. So that's one good thing. And by conducting early manual fire suppression, construction and airport commodities will have a higher chance of survivability. And oftentimes, airplanes are very expensive, and not only that, the insurance for the fire can become very highly prohibitive, as I'll talk about in a bit. And with this robust sensor system unaffected by fire and structural effects, one of the good things that can happen is property owners can return airport operations earlier. And also for the occupants and users, they'll be able to appreciate the continuous operation of the building. So economic evaluation is primarily just a secondary aspect of this from the environment and operational. Because of its capabilities, we can reduce costs of sensor installation for pre-existing buildings, and then its fire-resistant capabilities itself allows for reduced EOV effects and the reduced cost of forensic operations, mainly when you're trying to do post-fire investigation or scenarios. You get some professionals to check the building if it's occupiable or if it's highly damaged already. So in that sense, having an SHM system such as this that's not affected and is very robust, we'll be able to lessen the cost and not hire any of these fire forensics. So existing PEBs and other buildings can be fitted with SBS quickly with less resources. As I said, the mountability and maneuvering is all automatic, and so you don't have to have a fire department there to place and mount this, and this can occur from a distance. So even if there's no fire department on the site, it doesn't take time and effort to get to place this and detect the structural collapse. Post-fire forensics are actually conducted with SHM capabilities. And lastly here, early firefighting operations can reduce damage to property and altogether reduce the insurance claims. So to specifically talk about its sensing technology, I just some pictograms here, just from A to C. As I wanted you guys to focus mostly on C. This is where the sensing pipeline is gonna happen. So you have, as I mentioned, the sensor on a building, and the two sensors that's pretty common to be used together is the thermocouple as well as the accelerometer. So as these are as the fire scenario occurs, the thermocouple is going to measure the temperature. The accelerometer is going to measure the acceleration through the building, and as this main module, which is this module board, as you see here, has all the sensor capabilities, conductors that will allow this to detect whether there is going to be damage or not. And altogether, they also have this transmission from this wireless Wi-Fi module that transmits all the data acquisition from these sensors onto a PC from another location. As I mentioned, there's a lot of limitations from current sensor technology into predicting fire-induced structural failure and collapse based on visual imaging. And an infrared camera, it's not very highly effective, and the time between the first appearance of a structure deformation and actual structure collapse is typically too short to warn the collapse. So just to briefly talk about it, this is, apart from installing this during maybe at the beginning of a building construction, it can also be an emergency deployment system where at the detection of fire, one can just fly this drone and into the fire before you even deploy your fire department, so that while they're doing the fire operations, then you can detect when the building is gonna collapse. So with that time allotted, it's not much because, as you know, earthquakes and fires are very highly dynamic, and there's just not enough time to warn the collapse. So to have a drone that's automatically flown would really help and lessen that amount and increase that survivability aspect of the building. The presence of hot smoke and flumes and water for suppression during fire can also hinder the accurate evaluation of thermal signatures. So this puts on another aspect of EOV. The plumes itself from the fire can detract the visibility, and as well as affect how the SBS sensor can transmit and make accurate detection features, as well as the water. Water itself with electricity doesn't really fly, so it may actually become ineffective and not work anymore after the fire department has suppressed or partially suppressed some of the some aspects of the building, which can make this sensor ineffective. So this sensor method is based on detection of structural vibrations, acceleration, and temperatures, and make it a more accurate diagnosis for structural health status. So the SBS is integrated with accelerometer as a key element of the sensing. And a thermocouple is extended through a whole of the sensing module's case to the bottom of so that it can measure the temperature of the contacting surface. The accelerometer and thermometer are connected to the main board here, and the data are wirelessly transmitted or received via Wi-Fi connection. And then there's two lithium batteries are connected in series and used as a power source, and a GPS can be installed as a sensing module as an optional element. So that's typically the pipeline of how the sensing technology is conducted from application to transmission. And here are just the various types of modules that I just mentioned. It's sensing range, as well as the maximum operating temperature. One thing I wanted you to note for the subsequent slide is this power supply has the lowest maximum operating temperature, so at about 60 degrees Celsius. So now let's talk about feature selection, extraction, and metrics. So to start out with the selection, so when we're talking about feature selection, that's just determining which features to use for damage detection. And how we can validate that is for the experiment we're using sensitivity studies or empirical studies, and the metric used here is receiving rate. And so this receiving rate is kind of like just a transmission rate from the application to the remote place and where the damage is detected. And so a lower receiving rate means that that is probably an inaccurate data point. So we emit it, and a data detected with a higher receiving rate is most likely considered. So yes, it's a little bit empirical, but that's how it's done currently. And then so 100% receiving rates means that SBS features are not damage sensitive to environmental and operational variations. So as you can see here, in A, you have this transmission performance. As it's shown here, there's 100% receiving rate, so which means it's really good for transmission. And then for the bottom part here, we tested as well as like its insulation performance with 3 configurations at ambient normal temperature. When there's a heating happening at the bottom of the plate, as well as this entire surface heating throughout in the furnace. And for all 3 conditions, it's validated that the sensors can transmit 100%. So that's pretty good, and that means that if it's deployed in the field, we can also do the same. The paper mentioned they can also do the same thing, and that it's not affected by the EOV. It's in terms of extraction. This means to determine damage correlation for equipment functionality, and this is just to improve the effects of the thermal insulation. So how this was conducted was a comparison between the actual experiment as well as the finite element analysis FEA model. So physics based. So the metric used here is for as I mentioned, the lowest maximum operating temperature, which is associated with the battery. And so a lower temperature, lower than 60 degrees Celsius, means that it's a good insulation functionality. We'll be able to have a functioning sensor. If anything that's higher than that, maybe affect the battery. And altogether, that's really a critical point, because minimum temperature, and that can be the weakest link that will not allow this sensor to work. So that needed to be accounted for and validated. So in order to do that, you can see here that that for B here shows when there's the minimal effect of a burning at the bottom of the plate. This C here is where all the surfaces are being burnt, and D here is showing the comparison of of both of those. And E, so for B, C, and D, these are for the actual experiment, and E at the bottom here shows the FEA results. So for the B, C, and D, you can see that the 60 degree threshold is not exceeded, and it is matched with this FEA result, which shows that this really large blue section is where the lowest temperatures occur, which is roughly around 60, or can be assumed and estimated at 60. So there's a really great validation between the actual model, device, as well as the physics-based model. So kind of related to that is data normalization. So data normalization is a way to validate if your sensor works and functions well in the presence of an EOV. For our case, there's different approaches. What was utilized in this paper is to improve the SBS functionality for the attachment and impact modules in the presence of the EOV. So it's not really a field application, but more of like just a testing validation. But it can be applied either way, data normalization, and it is quite empirical rather than statistical, and we'll talk about more in a bit where this can be improved for this device. Maybe instead of just doing an experimental approach, you can use a data-driven approach in data normalization. But just to talk about these two things, so the top here is for the impact, and then the bottom here is for the attachment module. So the attachment module required an initial adhesion from magnets and secondary adhesion from inorganic adhesives. The main reason for that is during this empirical experimentation, the magnets rapidly lose permanent magnetic properties when exposed to high temperatures exceeding 500 degrees Celsius. So what needed to happen was this secondary adhesion material that consists of silica and alumina, which have highly fire-resistant properties that maintain adhesion well up to 1100 degrees Celsius. So, and secondly, the impact module, it required impact resistance from aluminum support as well as memory foam. The aluminum support is for the bearing between the sensor module as well as the memory foam attachment. And then for the memory foam, it consists of viscoelastic polyurethane material, which also as well has a high thermal as well as impact absorbing properties. And just to explain briefly what the results show. So for the attachment module, I want you guys to focus on this graph just a bit. So the blue here, the blue here is the effect from just the magnet. So as shown here, it does reduce. So initially it's good, but as the time goes on and as temperature increases, it does lose its adhesive effects. So the red here is the inorganic adhesive, which maintains a linear effect of its natural fire resistance. So as you can see from the black, it's more a superimposed combination of the blue and the red, where you maintain relatively a good adhesive force throughout the duration of the fire, per se. And then for the impact module shown here on the top, without this memory foam, which is shown in D here, you can see that as this drone drops the sensor down to the PV surface, it has a very high impact, about like 600 Gs. But then as you attach the memory foam, which acts like a shock absorber, it reduces that amount to about 50 Gs. So which is good. So as I mentioned, so the aspect that's a little not accounted here is the statistical decision or statistical models. Or upon review, the SBS technology contains no data-driven or statistical-based models. It's still quite in the beginnings. The data acquired from the experiment for sensor feature validation and application testing are all empirical. There's still no machine learning algorithms that are mentioned to analyze the data, even to do the detection itself. Is quite manual and not fully automated. So as you can see from what I've already mentioned, the data detection from the SHM sensors are queried manually. So even though the Wi-Fi capability of these sensors can be transmitted automatically, someone at the other end still has to validate whether a threshold, this damage threshold, is exceeded from the graphs that I mentioned. If they're exceeded to a certain point at which you would notify the fire department, or not if the damage threshold is not met. So that's one thing that is not so good with the system yet. It'll be great. Maybe they just did not mention it in the paper, and maybe they did. But I did do some investigation, literal review, and for the most part, there was only this paper that I found. So I think that's one of the disadvantages of this SBS sensor. So now let's move on to application challenges. So for application challenges, upon review, I would say the SBS technology may have a deployability challenge. And as you can see here, I just included a pictogram of one of the ways that they tested this, and it was on a PAV. It was a scale model. It wasn't even the real model. So that may be an issue all on its own. They didn't test it on a full-scale model. And as you can see here, there's also only a flat surface of a PEV, because you need that for the bearing capabilities of the memory foam, which is flat, has a flat surface. And also if you look at this PEV, it's a very regular looking structure. So oftentimes you've seen buildings, highly architectural aesthetical buildings, they don't really resemble this type of profile. So that might become an issue. So just to read about it, the validation experiments only presented application success for PEV structures and may not be extrapolated to other structures. PEV structures are short, they're one story, with easily maneuverable wall, floor, and roof profiles that do not present challenges for drone to place this SBS. And highly aesthetical complex building profiles without a flat surface with multiple appendages. Appendages are just if it has a lot of protruding elements that may obstruct the maneuverability of this SBS placement. And underground building profiles may have low visibility. So this was tested during the day, and maybe you can implement night vision for the drone. But then again, you also have this Wi-Fi connectivity for underground buildings that you may have that issue to maneuver this SBS placement appropriately. So this drone utilized for SBS placement needs to be validated in the end for its deployment and for adverse fire conditions. As you can, I'll show you guys in a bit from during the fire test. The conditions were quite minimal. It doesn't really account for all the fire conditions. Maybe it's a wildfire, or it can be a very drastic interior fire that can maybe affect the condition of this drone and not allow it to place this SBS correctly into the building. So that's just a few of the challenges. Now to talk about the results. So the SBS was tested, as I said, on a scaled model, and it was deployed onto a roof of a building. And as you can see on A here, it survived the initial, also survived during the fire, and then the collapse, as well as when the fire department went there and extinguished the fire, it wasn't affected, and there was no physical damage. So that's pretty good. And you can see from B here is a temperature profile as the fire grew up to 800 seconds. We can see that there's going to be some peak acceleration occurring, and then eventually you get some fluctuations, which induces structure collapse. But in the end, as we see here in E, all the sensors are still operational. So some of the conclusions that we can say is SBS is a mechanically and physically robust system that prevents key sensing elements from being damaged from fire. Because it survived a fire-induced structure collapse of the PEB from before, as I already mentioned. SBS is an adequate SHM system because combined temperature and acceleration data correlated data detection and structure failure. SBS has a versatile thermal resistance as well, and can be increased by lowering the effect of the weight as well as adding insulation thickness. And altogether, to summarize that, SBS can be remotely deployed to target locations of the PEV structures without physical damages, firmly adhere to the PEV surface, and ultimately predict collapse of a structure in a fire. So let's talk about how I would evaluate this, what are its advantages and disadvantages, and what can I recommend in the end. So to summarize, this SBS sensor is quite great. It provides a very easy and immediately emergency deployed device installation. It is highly good for temperature durability. It's highly sensitive, good damage sensitive sensor, which is not affected by EOV. It has wireless data transmission, which is great for remote sensing, and stable surface attachment, which adheres to a good amount of surface materials. And by using this on-demand deployment strategy, the extensive cost for installation of sensors in existing PEVs can be saved, making this SBS HSN system more economically affordable and practically accessible. But there are some shortcomings that come with it, as I pointed out briefly during the presentation. One of them is that damage detection requires user to manually carry the damage threshold, as I mentioned, and notify the fire department. You can probably surmise that because they didn't really talk about it in the paper. It'll be great to see if it's automized, because then there's no human error in whether this damage threshold is exceeded, as well as if it doesn't get exceeded, but it's a false positive, then notifying the fire department or not notifying them may become fatal. And secondly, the drone deployment requires a flat surface onto a PEB building, which is highly regular. doesn't have a lot of complexity involved, and it assumes minimal fire conditions. Just to go back here, as you can see, this isn't an explosive event. Sometimes you can have that, and this isn't engulfing the whole building. It's like maybe it started in one location and propagated, and nothing. It's you can still see some of the structure here intact, so it's not very an adverse fire condition. So, and then a lot of times maybe that can destroy the drone, or it can destroy the SBS system itself. So some of the recommendations I would say to improve on for future studies is maybe we can create a statistical decision model, and that can automate and classify damage detection, novelty detection. That can say, okay, is this undamaged or is this damage, and do we have what's the extent of the damage, and to what location should we send the fire department? And then secondly, we should provide more validation experiments, not only for PB buildings, and it's a great start, but maybe we can use it for other buildings that have more highly complex architectural profile, and either that or underground structures. And as well as the main focus that really didn't get addressed that much was testing the drone deployment for other surfaces, other profiles, and during adverse fire conditions. So with that, that's it for my presentation, and this is the paper reference. And if you have any questions, please send them to me, and thank you very much.